Okay, so hi everyone again for this session, the second session for electrodynamics. And before I go for today's topic, if you will have any question, then please unmute yourself and I will try to answer some of them if it is from the last session. Anyone?
No.
Okay, there is no question. So what we discussed in the last session, because I just said that I can spend almost like three sessions for units and vector analysis. But probably today I'm going to finish this vector analysis as well, because already units have been discussed. And most of the details of this vector analysis is going to be covered with examples and numerical problems in the mathematical physics courses. So I will just, because I introduced this, because I should be very clear that what symbol I'm going to use for our purpose. Okay. So let me just recap in few minutes what we did. So we talked about electrodynamics and correlated with the general physics, where we talked about that how classical mechanics, quantum mechanics, special relativity, and quantum field theory are parameterized by two components. One is the size and one of the speed. Then after we discussed about the picture behind these kind of development with respect to fundamental forces. And then we also talked about that why unification is necessary for the physical theories, and some of the things which we discussed in respect of electromagnetic force, where we know that electricity, magnetism, and optics were combined together, or you can say unified together, was the very first picture among the unification of physical theories. Similarly, then we talked about the standard model, where I gave just a very brief picture that how this electromagnetic force, weak force and strong force was unified. And nowadays in the colliders, we almost have a very great significance of all the particle content of the standard model discoveries and all those things. And then after we talked about that why not gravitational force was unified, and then the solutions comes from various high dimensional theories like string theory, grand unification theory, etc. But these are not established yet very beautifully, but we hope that we can have something around this where quantum gravity can also play a role with the graviton, etc. And then we talked about the field formulation of electrodynamics, and where we described about the charge. And then we talked about that the property of charge should contain either positive or negative, should be conserved, and also it should be quantized. Okay. And we're going to see these pictures in more detail when we go for the third session, where we basically talk about the electric fields and all those things. And then we also discussed that quantization at the quark level is going to be more smaller than the but since these are confined within the proton and neutron, so I mean it doesn't matter that you can have a fractional charge as well. Then we talked about SI unit and the Gaussian system, where we discussed how Coulomb's law is going to be represented in SI and Gaussian units, and the conversion factor is coming like epsilon naught should be going to be 1/4 pi, which should be annihilated in the charge itself. And similarly, one can discuss the energy in the electric field system in these two units. Therefore, Via law is going to be also defined in terms of these two units. And we talked about Lorentz force, and then the electric field in the energy in electromagnetic field also from Gaussian to SI units, one can have this. So these are very important things when we talked about competitive examination, and also for the general notion of understanding about the conversion of units from SI to Gaussian system. And this is the whole list where, I just put it there so that these conversion factors could be remembered and could be used further when we need actually. Then after, these are some convention and notation, and I'm going to follow throughout by Griffith's book, and so these are discussed in detail. Then after, we started with vector analysis, where I just summarized that what addition of vectors, two vectors means, also multiplication by scalar, dot product of two vectors, and the significance of that why it is important, when it's going to be perpendicular, when it's going to be parallel. So these are some of the things which is very important and very preliminary. Even in class 11th, you have learned this thing. Okay, but just for the definitions and the notations, I just wanted to revise this part where we also discussed about cross product and all the properties which is related there. And these are very important even for many problems which we're going to solve once we start. Not only in the mathematical physics, the significance of these formula is significant, but also for the calculation purpose when we go in electric field calculations and related problems, then we're going to use these things very frequently. So these are some of the properties which we learned. So let me go faster and faster, where we also define law of sine and law of cosine. Then we talked about vector algebra and how we can represent in a coordinate system, and especially in the Cartesian coordinate system. And there we defined a system where we have a three-dimension space coordinate belongs to x, y, z within a right-handed system, the right-handed Cartesian coordinate system, and x cap, y cap, z cap is going to denote the unit vector in the direction of x, y, z respectively. And when we define a position vector for any vector A, then we can just draw like, first go through the x component ax, then go to parallel to y axis, which is ay y cap, and then go up with parallel to z, and you want to get az z. And you can represent this vector as vector A equal to axx plus ay y cap plus az z cap. So these are very basic things which I represented. And then the very important thing which we talked about is the sum of these two vectors. And then we saw that component wise we can always add the vectors. Like if you have a x direction component for these two vectors, we add up, and then we can put a multiply with the unit vector direction, etc. Okay, so then we learned about the dot product of the unit vectors like this, and we know also why this is going to happen. So I mean, I'm just skipping this very fast. And then we learned about the cross product, etc. And then after, so let me go very basically. So we did up to this, and then we define something like dot product with the cross products of three vectors, something like this. And this could be represented in terms of the determinant, and accordingly we can discover the formulas like A cross B cross C should be equal to B times A dot C minus C times A dot B. And these could be proven very easily by just considering, if you consider, for example, your vector A is something like this and vector B is something like this, you can always evaluate this right-handed terms and left-handed terms, and you will see that this is going to follow this certain rules. Okay, and these are some of the things which is very important. So today I'm going to just give you a brief overview of position, displacement, and separation vectors. But before I go here, I mean, I would ask if there is anything you need to remind me, which I forgot to mention or something like that? Or if you have any question from the previous, because this was up to slide number 9. I just, gave the overview what we discussed in the last session. Anyway, if you have any question, almost you are welcome to unmute and interrupt me. Okay. So when we talked about position, displacement and separation vectors, I'm going to use the symbols, which is, so let me now keep my laser pointer. So if you have a three-dimensional structure like this in the Cartesian coordinate system with the right-handed coordinate like x, y, z, as you can see, and any point x, y, z can be represented by a position vector, which we call r vector. Okay, and this r vector is basically contain the component in x, y, and z direction. So you can see here. So parallel to this, from the origin O, parallel to x-axis, you have this x distance. Similarly, with respect to y, you can have y, and z is given like this. So this point is the coordinates of this position vector r from the origin. Okay. So in vector form, you can define this r vector as x, which is written in the italic symbol. And then you have x cap, which is the unit vector in the direction of x-axis. Okay, and then you can add up the y-axis similarly. So here you can see that you have the y coordinates, so you can write plus y times the unit vector in the y direction, and similarly you can add the z direction like this. So this is known as the position vector, and you can define the magnitude of this vector as simple r equal to root over x square plus y square plus z square. So these are very basic things which you have already learned, but for the symbolic purpose, the symbol, when I use this thing, you're going to see that, I meant for this. If I just use r vector, that means this defines something like this. Okay. Similarly, unit vector for this position vector, which you can see here in the direction of r vector, there is a unit vector called r cap. Because if you take only one-dimensional structure like x-axis, you can say that in this direction you have a unit vector x cap. Similarly, in y direction you have a y cap, and in z direction you have a z cap. But here you can see, you can also define, since it is a vector, so in this direction, which is basically coinciding with the direction of the position vector r, there is a unit vector associated with it, and that could be defined very easily by having the r vector divided by the magnitude of this r vector. Okay, so this you can write. So just substitute this r position vector like x cap plus y cap plus z cap divided by the magnitude, which is root x square plus y square plus z square. Similarly, if you wanted to go for the infinitesimal displacement, which is very important when we talked about differential calculus, and and we're going to see these things in a very detail in terms of electric and magnetic fields as well, and we're going to use it very frequently. Okay, so if you have something like very infinitesimal displacement, something like, let's suppose you have an x coordinate here, and you wanted to just displace it by a certain amount. So you can say x plus delta x, y plus delta y, z plus delta z. Then the displacement from this point to that point is going to be defined something like dl vector equal to dxx cap plus dyy cap plus dzz cap, where sorry about that, where dx is basically the change in the corresponding coordinates. So this is dx represent here the change in x coordinate, dy represent change in the y coordinate, and dz defined as a change in the z coordinate. So this way you can define an infinitesimal displacement vector, dl vector, equal to dxx cap plus dyy cap plus dzz cap. Okay. And then by using this, you can always, I mean, in the 3-dimension, what we're going to use here, like something like the displacement vector, we can write in a curly vector r should be equal to vector r minus vector r prime. Okay. So something like,
sir.
yeah.
Excuse me, sir. Sir, here you used r is equal to r minus r dash. This symbol is what does it mean, sir?
Yeah, so it means the
R is equal to
displacement.
r minus r dash.
Yes, so this means we are going to take the displacement from origin. Let's suppose you have something like the same axis, okay, and you have, so that's why I draw here. So let's suppose you have some source point here, which you wanted to define with respect to some field point, and the displace and the position vector with respect to the origin is the field point is, let's suppose this is r vector, and from the origin itself, source point is something like r prime. Okay, so the difference, which you can calculate always very easily, because you know the vector algebra, that how you can how you're going to add this. So this is going to be r prime plus r equal to r vector, right? So you can always write this r vector, which is a kind of displacement, is defined as the difference between the position vector of field point and the position vector of the source point. Okay, is it clear?
Okay, sir, that means
Excuse
this
me, sir.
symbol means defining something.
Yeah, it is just definition. You can always write this. I mean, you know, maybe this r could be written as something like a, b, whatever you want. Okay. So, but we're going to be consistent with this symbol, because, you know, I am following one particular book. So generally when we write any expression like this, then I'm going to use this symbol. Okay. So that is it. Nothing extra. Yeah. Somebody else wants to ask
Yes,
something.
sir. What is meant by here? Means what is meant here by field point?
Oh, okay. So these things actually, I'm going to you know, explain in more detail when we talk about electric field. But let's suppose I'm just giving you an example. Here you have a charged particle. Okay, so this charged particle is known as a source point. Okay, but when we talked about the force between two particles, then what we say, we describe it by a field. You know, that one field is basically interacting with another field. All right, so let's suppose there is a charged particle here, so it will create a field, and you know, I wanted to calculate something around this point. So this is called the field point, where we wanted to calculate our observable, whatever we wanted to have, like an electric field, for example. So one example could be like, you have a source point here, you have a source point of some other charge here, and both are having the, you know, their own field, and I wanted to calculate their interaction at this point. Okay, so this is going to be more clearer when we talked about you know, in the second chapter, when we talk about electric field and all those things. All right, is it clear? I mean, vaguely.
Yes,
Yeah?
sir.
Okay, good.
Yes, sir.
Very good. So this way, when we you know, having our consistent symbols to define the displacement, and or you can say the difference between the source point and field point position vectors, like a small curly r, then you can always find the magnitude, and that magnitude can be obviously written in terms of the moduli. So this moduli is something like r minus r prime, and this is going to give you the basically the magnitude. Yeah. So, and then similarly, as we defined here the unit vector of one position vector, you can always define the position vector for the displacement. See, these things are going to be very important, because in the next slide, I'm going to ask something, and then we're going to have a very precise definition of something. So I'm going to disclose that, but let's focus on that, the terminologies which I am using here. Okay, so then I will ask some question from you, and then we will move towards the definitions and some particular issues which I wanted to discuss today. So by having this, as you say that the unit vector for some position vector is given by the position vector itself divided by the magnitude. So if you have a displacement vector like that, you can always define the unit vector in that direction. So for in this case, you can see the unit vector is going to be like in this direction, okay, which is going to be like coincide with the direction of this curly r vector. So by having this, you can always define that this is a vector r divided by the magnitude of vector r, which is equal to r minus r prime divided by the magnitude of r minus r prime. So in Cartesian coordinates, simply what you can write. I left some space here so that I can show you something before we go. So in any system, you know that. So let me just let's suppose you have a 3-dimension system like that, okay? But before we go for 3-dimension, I'll start with something like 1 dimension, okay? So if you have a 1 dimension, okay, some axis, let's suppose this is my x-axis, okay? And this is your origin, all right? And somebody start moving from origin and go up to some point, let's suppose A, okay? And after some time, you see that some observer at O see that someone is at B, okay? So what do you do? Basically, when you wanted to calculate something like the distance from A to B, okay, this person basically moves from A to B, then this observer want to see that how much distance it covered. So what he or she going to do, obviously is going to calculate this distance, okay, and this distance, and just do the subtraction from OB minus OA. So this is going to give you the distance covered from point A to B, okay? So in a coordinate system, simply you can say that this is nothing but x2 minus x1. So let's suppose I say this is x-axis, so this is x1 and this is x2. Then the displacement you can calculate from A to B simply like x2 minus x, which you did in very basic level of your classes, okay? So, but when you generalize it for 2-dimension, what is going to happen? So if you generalize, let's suppose you have a 2-dimension space, okay? So you have an x-axis here, and let's say this is y-axis. So now you define a position with respect to the origin. Let's suppose this is the origin. You define some position, something like here. Now this coordinate is going to have some value. Let's suppose this is x1, and then you can say this is y1, okay? So x1 always defines something like the distance from origin to this point, and y1 is defined the distance from origin to this point, okay? And then you can say the position vector in this is defined with these 2 coordinate x1 and y1. But now let's suppose the similar situation which we had here in 1 dimension, if we have a 2-dimension and particle moves somewhere here, okay? And now your coordinate system is something like you have x2 comma y2, okay? So that means in x direction, the particle moves something like from here to here, so like this point, and in y direction, particle moves something like from here to here, okay? So you can say that the position vector of x2, y2 is defined something like this one, okay? Now you wanted to calculate the displacement. How are you going to do this? So you're going to just match up this vector, and then you can say that this is nothing but x2 minus x1 whole square. So let me write it somewhere So that so this distance you wanted to calculate, or you can say the displacement, in a magnitude. You might have go through these things in your mathematics classes as well, that the distance is nothing but you can write something like x2 minus x1. So this is very basic, but since you wanted to have everything to remind myself, so I am just writing this. Then you can write something like y2 minus y1 whole square. Okay, so this way you calculate the distance. So similarly in 3 dimension, what you can do, first of all, you can have this something like this axis. So you can define, sorry about this. So this is x-axis, this is y-axis, okay, and then this is z-axis. So again, some point you can choose. Let's suppose this is a x, y, z coordinate, which you can always define something like this, that x is moving like in the some distance here, then y moving like this, and z move like this. You define the position vector. Similarly, when you have something like here in 3 dimension, you can define a position vector here. And by having the generalized notation, then you can say that the position vector or the displacement from this point to this point is defined as the difference of coordinates from this position to this position in the direction of x, plus in the direction of y, and plus in the direction of z. Then you can define the position vector of any vector in 3 dimension, something like this, which you can see here. Okay, and then you can also calculate, as I had shown here, that in 1 dimension it is fine, you can just have the difference. But in 2 dimension, that this is followed by, in general, you can also follow this by Pythagoras theorem, that how you going to find, basically you have if you have a right angle triangle, if you remember, then this hypotenuse is nothing but the difference of this coordinate square plus the difference of this coordinate square, root over. Okay, so root over, you can say if this is b, which is base, and this is p perpendicular, then you can say that h is nothing but a square root of p square plus b square. So this is the same thing in a generalized form, where you have to use the 3-dimensional space coordinates. Okay, and then the magnitude is going to be calculated like this, and then unit vector also again going to be calculated like the similar way which we did here. So you can just write it like this. So is it crystal clear to everyone, or are there any questions?
Yes, sir.
Very good. So these are very basic things, and we're going to use it very frequently. So that's why I spent a lot of time on this, so that these questions should not, come back again to me. But obviously, I would be happy to answer anytime. But this is my, introductory thing. Okay. So now let's move ahead. After this displacement, I would like to come back again. And probably you people also getting bored, because anybody is going to, whenever they start any class, especially on physics, they always ask what is the definition of a vector. So what is the definition of a vector? Can anybody repeat the answer? I would not say that nobody knows, but what is the answer in general?
A physical quantity which has direction.
Which has a magnitude and direction, right? So this is a very general notion where we say that a quantity with a magnitude and direction is known as a vector. But let's ask again, when we say about a quantity with a magnitude, this is fine. But when we say about the direction, what especially we mean by the direction? Okay, so precisely what direction means, or I would say that what is the precise definition of a vector? Okay, so I mean, this is a very relevant question, because now you are in an undergrad level and you must know that the property of a vector should have magnitude and direction. So this is just a property. This is not a definition. Okay. I would be very strict on that, and it may sound something like pedantic, but one should, and one must ask that what one mean by the by a vector. Okay. So in general, we can say that, okay, if you have a and which we discussed just like in the last slide, that vector is anything that has a 3 components and that combines properly under addition, and we saw that. Okay. So I'm imposing one example, and then I'm going to ask something there. So let's suppose, let me write it here. So let's suppose you have a bucket. Okay. And you have a different kind of fruits in this bucket. Okay. So let's suppose you have some fruit with the color blue, and then something, let me change the color again. Let's say this is magenta. Okay. And let's suppose there are the other things with the color something like, let's say, green. Okay. And we say that this blue have the number of, let's suppose this is apple. Okay, let's suppose this is apple, and I am denoting it by number like something like nx. Okay, and then they said we have peers with number like something called ny. Okay, and then we have something like, let's suppose, banana or something. So we say that this is nz. Okay, then we can always write this vector n. I mean, the notation which we have used so far, that we use generally bold letter, but in general when we write in a copy or pen and pencil, we always put an arrowhead for a vector. Okay, so then we can simply write that this could be something, we call it an x in x cap. Okay, this denote apple. We can say that you have ny, this denotes pears, let's suppose. Okay, and let's suppose this nz is banana. Okay, so according to the definition which we just learned, that vector is anything that has a 3 components. Can we say that this is a vector? We can write, right? Because this bucket contains 3 types of things. Okay, we say that apple, pear, and banana, and then number of apple is nx, number of pears is ny, and number of banana is nz. Then we can always write this as, okay, I mean, we can write this in vector as nxx plus nyy plus nzz, where x denotes apple, y denotes pears, z denotes banana or pineapple, whatever you want. Okay, because this has 3 components, right? So can we say this is a vector? Tell me.
No, sir.
And why so?
Sir, because of their direction.
Because
There
of
is
the
no
direction.
precise direction.
Good. So that's why we have to focus that what direction basically means. Okay. But somebody can again say that, you see, I mean, this bucket also, because this is a very beautiful things, I mean, try to understand one by one. I'm spending time on that. Let's suppose again, the definition which we learned so far, this is also going to reveal something to us. Okay. So far what we have seen here, before coming to the direction, that a vector we saw like this should have a 3 components. Similarly, if we combined properly under addition, what that means, let's suppose you have another bucket. Okay, let's suppose let me not use any different color. Let's suppose again we have another bucket and filled with again something like mx of mx number of pears, my number of apple, and mz number of banana. Then again, if I sum it up, obviously we can sum it up because we can write like n vector we wrote, we can also write m vector, right? And when we sum it up, we can say that here we have, let me sum this, okay? We say that, okay, this is something like nx plus, mx, okay? Similarly, the y component will be ny plus my, and z component will be nz plus mz, okay? So this also, if one should just see that how we represent the vector so far, and somebody wrote something like this, we can always say, since we know that vector is anything that has three components and combined properly under addition, then we can say that this is a vector. But as we had already answered, that this is really not a vector because we don't know about the direction. Okay, this is not a directional quantity. Okay, so in physics, this is very important to have a precise definition of the direction. I mean, or we can say in general, what is the precise definition of a vector? So to have this, you might have remembered in previous slide what we did. Whenever you write a vector, you always denote it by a coordinate system, right? So even in one dimension, we say this is, somebody is displaced from origin to some point. We say that this is a coordinate system in one dimension. Okay. Similarly, if it is two dimension, I mean, the object is moving on a plane, just like a surface of your, surface or roof of any building, then we can say that, okay, I mean, we have to now define a two-dimensional coordinate system. But if something is in air, then we say that, no, we have to define a three-dimensional coordinate system. So this is very important to understand here, that we define a vector in a particular coordinate system, okay? And that's why we need to know about one of the property called a transformation, okay? And that's what I'm going to precisely define here. So to define the thing which I just said, I just wrote it here. So to define a vector precisely, we have to consider how a vector basically transforms when we change the coordinate system in which it is represented. Okay, so let it put like a question to us. Can anybody answer this question? Which the statement which I wrote here, can anybody answer? If it is a question to us, like a vector, precise definition of a vector is only when we consider how a vector transforms when we change the coordinate system in which it is represented. Okay, so if it is a question, how are we going to answer this? Does anybody have any idea? Or you read somewhere about this? Say yes or no.
Sir, can you repeat, sir?
Yeah, so if you see the statement here, you understand, right? I mean, what I said before, that in general, we had a vector, something with the three components, and they should combine properly under addition, okay? But then we took this example and we say that, okay, I mean, we can do that, but we can't say that this is a vector, okay? Then directly we ask the question that what direction actually means. And then we particularly talked about that whenever we define something in space coordinate, then only we define something called vector, okay? Something like in x direction, if something is moving, we say that, okay, yeah, this is a vectorial quantity. Something in y direction, then we can say that, okay, I mean, if it is a plane, then we define in a two-dimensional coordinate system. So basically, once we talk about the direction, that means it is something called a transformation, right? Transformation of a coordinate system. All right. So anyway, so let me try to answer this, and hopefully you're going to also, after this lecture, please don't, whenever people say that what is the definition of a vector, obviously you can mention that a quantity with a magnitude and direction, but additionally you should also talk about something under the transformation of the coordinate system. You must need to define a vector. So what is that? Let me go through it, and then probably if you have any question, we can evolve with that discussion. Okay, so let me go through it. So how vector transform? That's a very important question. Okay, so for that, let's suppose you have a three-dimensional coordinate system x, y, z, or for precisely for here, let me say only two-dimensional coordinate system, and we can generalize the definition in three dimension afterwards. So let's suppose you have a two-dimension where it is defined as a z and y coordinate, okay, with our notations and all those things. And this coordinate system, in this coordinate system, we have some vector called some a, okay, which is a position vector with y and z coordinate. And this makes angle theta with respect to the y-axis. Now rotate this two-dimensional system with some angle called phi. Okay, so once you rotate it, what is going to happen? Obviously, it will, since this is 90 degrees, so obviously, you will get this angle like phi, and also this angle should be phi. And then you have a new coordinate system, something called y bar and z bar. Okay, and then now you can see that if you define this vector a in this zy coordinate, what could be the component of a? So you can say that ay is equal to a cos theta and az equal to a sin theta. This is very clear, right? Everyone understand this? Yeah.
Yes, sir.
Yeah. Okay. Now you transform it. So after transformation, what could be your ay bar? Can somebody tell me? Now it's a very simple. Yeah.
A cos of theta minus phi.
A cos of theta minus
phi.
Yeah, because in this representation you have a theta bar here, which is making angle with a y bar axis. Okay, so now you calculate immediately theta bar, which is theta bar is nothing but theta minus phi. Okay, so you can say that basically, well, I mean, for example, if you don't have this coordinate and you have only this coordinate system, then theta bar can be represented similarly like what we did in the zy system. We can write this ay bar in the z bar y bar system. So we can say that this is a cos theta bar. Okay. Now, this, as you said, that this theta bar is nothing but theta minus phi. Then you can write that this is a cos theta minus phi. And from mathematics, from trigonometric knowledge, that this cos a minus b can be written as cos a cos b plus sin a sin b. Okay, so you can expand it and you can say that ay bar is nothing but a times cos theta cos phi plus sin theta sin phi. Okay, where theta is the angle in the zy frame, and phi is basically the difference between these two the rotation coordinate system. Okay, very good. So, or what you can write from this formula, that a cos theta is nothing but ay. Okay, and similarly az is equal to a sin theta. So when you multiply this, a cos theta can be represented as ay, and cos phi remains like this. And then similarly, you can say that a sin theta is az, so az times sin phi. Is it clear to everyone what I'm doing here?
Yes, sir.
Very good. So then after, this is ay coordinate, ay bar coordinate. in the rotated frame of reference. Okay, and this rotation has been done with respect to the origin with the coordinate system zy. Okay, now similarly you can write for az bar, okay, which is very obvious because this is just like this component, and this component is nothing but sine theta bar. So a sine theta bar is az bar, and then again you can write theta bar as theta minus phi, and then you use sine a minus b formula, and then after you know that sine a minus b is sine a cos b minus cos b sine a. So you can write this by using trigonometry, and then by using again this notations where ay is a cos theta and az is a sine theta, you can say that you can have az bar as minus sine phi ay plus cos phi az. So with this beautiful relation, what do you find? What is our basically the notation? I mean, in terms of matrix, we can always denote that ay bar can transform into the component ay and az. Okay, similarly az can transform in terms of ay and az, and that is the real thing that one must know, that vector basically should transform under some coordinate space as a displacement. Okay, and displacement is just a kind of one model which we are discussing here. But when we talk about linear algebra term, when you go for the mathematics classes, you must have learned about linear algebra. There the vector space is a very very widened, and this is one of the, you can say, one of the example of those linear vector spaces. Okay, and probably in mathematical classes you also going to learn those things. So in 3 dimension you can generalize it, and you can say that these terms can be a combination of cos theta, cos phi, etc. And then you can write simply as a matrix where you can say that this is rxx, rxy, rxz, blah, blah, blah. And this could be like a homework for you, that you should find what could be the value of rxx, rxy, rxz, which you can do very easily. Okay, so try to do this as a homework problem. And if you have any question on that, if you unable to solve this thing, then let me know again, by email or whatever, and then I will discuss this in detail, that how one can go for the 3-dimension system like this. So this is a very interesting property. Let me check. Yes, certain. Yeah, very, very nice. I'm coming to that point. Okay. Yeah. So, so in general, because I mean these notations are going to be very, very helpful and useful for your higher level of transition. So that's why I use the summation formula, where Rij is nothing but matrix with I and j component, where j can go from 1 to 3, and you can always write a ai. So you can see this is just a compact notation in 3 dimension. So if you say ax bar, then I is basically x. So you can say this is x, and then you can have this x and j go from 1 to 3 like a sum up. So you can write something like this here. Okay. So these are some of the notations which I'm going to be used to when we go for, in a very detailed manner. Okay. So by having this knowledge, what we can say, so now please remember, okay, you are in undergrad. So whenever somebody will say, what is the definition of a vector? You can simply say a vector is any set of 3 components that transform in the same manner as a displacement when you change the coordinates. This is the precise definition of a vector. Okay, so, and you can see that in this definition, I quoted unquoted this part, which is called model. And model basically defined in this 3-dimensional set, where you have a 3 bases of the 3 basis vectors, which we call x cap, y cap, z cap. But when you go in linear algebra, the basis vectors will be, infinite. I mean, you can just go like A, B, C, D, etc. Okay. And then there is a generalized coordinate system which you need to talk about. Okay. So this is a very precise definition of a vector, which I wanted to, tell you. Okay. So in other words, there is one more terminology which we call invariance. Okay. So let's try to see this by the same example which I showed before, where we talk about something called a scalar. Okay, so far we talked about a vector, but if it is a scalar quantity, what is going to happen? So let's suppose you calculate the magnitude. Okay, so this magnitude of this vector A in the zy coordinate is going to be same in the yz z prime y prime coordinate. Okay, or let's say z bar y bar coordinate. So you can see now the scalar quantity, which is the magnitude, is not transforming something like, which we transform here, that ax bar can be a combination of ax, ay, az. Okay, that means ax can transform into the other components as well. Okay, but a scalar quantity cannot. Okay, so that means when we say scalars, one should mention that a scalar, generally we say that, okay, scalars means just a magnitude. Okay, but no, now we can say that a scalar quantities remains invariant means unchanged under any transformation of coordinate systems. Okay, this is very, I mean, maybe it sounds like pedantic, but we have to digest this definition. So let me stop here for, if you have any question, then I will again, define these things and tell you if you have any question regarding that. Is it clear to everyone?
Sir, can you repeat that scalar once again, sir?
Yeah, so you can see here what we did when we do the rotation of coordinate system. What you can see that ax bar can be a combination of ax, ay, az, right? That means under coordinate transformation, it is not invariant in one sense. Okay, that means obviously in one of the lecture, maybe in the mathematical physics, you might have gone through the transformation in a linear transformation and all those things. But here we basically talked about a transformation where my coordinate space is basically changing, or rotating. Okay, so if you compare now these two definitions, what we see here, that a vector is any set of three components that transform in the same manner as a displacement when you change the coordinates. But under this change, the magnitude of this vector is not changing. You see here. You understand my point? I mean, you see, I mean, any position vector in this zy direction, in the zy plane, is going to have a same magnitude, and also in this reference frame where you just have the angle, this magnitude is not going to change, right? So it is something like you have mass. You calculate the mass of a body, okay, in this yz coordinate, and also you calculate the mass of this body in different coordinate system, something like z bar, y bar. What is going to happen? Mass is, if mass is 10 kg, then it is 10 kg. That is it, right? So when
Yes,
you
sir.
calculate, so when you calculate this magnitude of this vector A in this coordinate system, if you have a three-dimensional coordinate system, then you can calculate simply like, okay, root over x square plus ay square plus z square. Similarly, in some prime coordinate, you can calculate the magnitude as this, but these both are going to be equal, okay? And that's why the scalar is going to be invariant quantity. And we're going to see, because you see why I'm giving you so much of time in that, because we need to construct such kind of vectors, when we basically going to combine electromagnetism, like electric field and magnetic field. You will see that there is something called E dot B, which should be invariant under coordinate transformation. Okay, so these topics are going to be very useful. So that's the definition, So now you are, whenever somebody asks you the definition of a scalar, definition of a vector, please remember these definitions must be put in. Okay. Any more question on that?
No, sir.
Very nice. Very good. So probably you enjoyed this topic, and let me now quickly, because most of the things is going to be covered in your mathematical physics classes. So I will not touch upon those, but for completeness, I'm going to talk about a few things which I'm going to use very frequently in this course structure. Okay. So first thing is very minor thing, which the differential calculus, where that ordinary derivative can be written as df equal to df over dx times dx. That means if you have an infinitesimal change, then that change can be give you some kind of you can say the slope of a function, and that slope can be either frequently moving or slightly moving. You can always determine by calculating the differential object. Okay, so something like let me draw a function. For example, you have some function which you wanted to have you drawn, and you see that this is fluctuating like this. So you can say, comparing to this, if some function is something like this, you can say that this function is moving or changing more frequently comparing to this function. Okay, and the reason is that at each point you just calculate the tangents, and you can see that this tangent is basically more higher and higher comparing to what we have here. However, at some point of time you can see there is some difference, etc. So you know about this ordinary derivative, so I'll not go into the detail of that. So by having this into our like in concept, we calculate gradient, and gradient in itself says that this is just measure of, if you calculate the magnitude, basically it is nothing but a slope of that function. Okay, so something like this. So if you have some function t which depends on x, y, z, so basically this function t here is the function of x comma y comma z. Okay, so this is a directional quantity, or you can say this is defined in 3 dimensions. Okay, so something like that. Then you wanted to just calculate a change. Okay, so let's suppose you calculated something at this point, and then you wanted to calculate this same thing, the same quantity at this point, where your t is basically going to be like something like t prime, because now you have coordinates which is going to change, and that change is defined as something like x plus dx. Okay, similarly you can define y plus dy and z plus z, blah blah blah. Okay, then you can calculate the change dt in terms of the partial derivative of t with respect to x times the change in the x coordinate. Similarly, you can write for the y and z coordinate. So gradient is basically defined, and in the last lecture, I think in mathematical physics, you gone through this, so I'm not going into the detail of that. So let me erase it so that you can see what I wanted to show. Okay. All right. So you can write always this, this quantity in terms of the position vectors and all those things which we defined just now. And then after, you put it automatic. So you can always write that this is just change in the x direction. So you can use it like x cap, y cap, z cap, and this dx, dy, dz can be written as the position vector dxx plus y dy like this, and then the dot product. And you know that the dot product of x cap is 1, However, it is going to be 0 if you have x cap, y cap, y cap, z cap. And by using this, you can, come back to this formula again. But this differential is going to have a very basic definition. This already we defined. Okay, this was just like a displacement vector. So this is going to give you another very interesting thing, which we called something like delta t. Okay, and then you can write this as a dot product of two vectors. One is delta t times the dl vector, where dl is the displacement. And that's why these notations are important. I already introduced that whenever I write dl like in bold letter, then we meant like dxx plus dyy plus dz. Okay, and then this delta t is again a vector, which is delta basically is a vector which can be written something like this. Okay, so this is called gradient. And so we can say the gradient is nothing but for delta t points in the direction of maximum increase of the function t. And what that means, that if you can write, I mean, let me just elaborate more. So you can always write this as a, this is delta. So whenever we write by hand notation, we put arrow over the vector quantity. So you can write delta t, you calculate the magnitude, multiply with the magnitude of dl vector. And you can say, since this is a dot product, so this could be like cos theta. Okay. So now for theta equal to 0, you can say this is going to be a maximum quantity. Okay. So that's what we mean by this statement. So this statement says the gradient delta t points in the direction of maximum increase of the function t. Okay. And moreover, we can say that when we calculate the magnitude of this delta t, it means it is the slope or rate of increase along the maximum direction, as we had just seen in the function where we talk about the differential derivatives. We basically call about the slope. Okay, so similarly here this delta notation is used as a vector, and this indicates the slope along the maximum direction. So you have learned this in a very detail. Actually, I saw in the last lecture on mathematical physics you have done, but I would refer to you people that please solve a lot of problems on that. Unless you solve the problem, you're not going to understand these topics very easily. And I hope in mathematical physics classes you're going to dwell with the many such problems. So that's why I'm not giving here any problem, because my reason is that I should go for electric field, etc., where we're going to use this thing, and there I am going to give you more and more numerical problems and understanding of all those concepts. Okay. So yeah, so the thing which I wrote, actually this is written in terms of this. Okay, and therefore this del operator which I talked about can be written as delta equal to x cap del over del x. This is just a partial derivatives, and you can go in three-dimensional space because we are talking about the three-dimension here. So delta is a vector operator that takes upon t, as we had seen here, and not a vector that multiplies t. This is very important statement that one has to understand. So after the definition of vector and scalar in terms of the invariance, we say that vector is something which should follow the law of addition. We should have a three components. We should have a coordinate transformation under which it should act like displacement, and etc. Okay. So now you can say that, okay, this del operator is delta is also a vector. So should we say like, should we do this thing something like the vector which we did? So here we need to be very cautious that this is a vector operator. Okay, this is something which operates over some some t, because here we talk about t. So it is acting on something, and that's why we call it as an operator. Okay, and this is nothing like, we can say that this is a multiplication of this with t. Okay, so be careful when we say about the del operator or ingredient. When we use this, we call it an operator, not simply like a vector which multiplies with t. So be careful about these things. Okay. So in one sense, when we say operator, in quantum mechanics also, we're going to see these things. It is something like you have something, let's suppose you have a tomato or something like that, and you operate something like here. And what is going to happen after some time, you will see that the shape of this tomato is going to be fractured, or something like this is going to happen because you put this operator over there, and this changes the shape. But since this is a tomato, so you can say that this is a tomato, and still it is a tomato, but now the eigenfunction or eigenvalue is basically changed because of this operator. Okay, so operator means something very, very diligent, and we should not mistake it something like which is going to be multiplications of something like that or so. So be careful about that. All right, so
Excuse me,
because
sir.
yes, please.
Sir, what operator does to a vector then?
Yeah, so this you can see here. No? And this del is going to be, so probably you asked the next question, which I'm going to tell you, that what basically del operator do when it acts on a vector. Okay, so this was just like a scalar quantity, and it acts on that, and we see that this is overall a vector. Okay, but when we say about this, so that's the next thing which I'm going to actually tell about. So let me just first erase this which I draw, then I'm going to answer your question. Right, good. So first let's know the property, what is going to happen here. So if you have an ordinary vector A, okay, then what you can do, if you multiply by a scalar A, simply you can say that this vector is multiplied by A, and this is, you can say that by that multiplicative factor you have scaled that vector. Okay, so let's suppose you have a vector A, something like x cap plus y cap plus z cap, and then you multiply with a factor of 2 overall, then you can say that it is twice of that vector. Okay, similarly, if you have a vector, then you can write the dot product something like A dot B, and you can write a cross product something like A cross B, which we already learned. But when we say about this operator, what is going to happen, that on a scalar function, when it acts, it says like a gradient. Okay, you see the difference now. Okay, and so this is going to answer your question which you just asked. So when it acts on a scalar, you can see an ordinary vector just multiply and they scaled up this vector, simple like multiplication, but this is defined as a gradient. Okay, so if you take the magnitude, you can say that this is nothing but a rate of increase, or you can say the slope, because this is a differential operator. This is a difference. Okay, then you have an ordinary vector. However, when it acts on a vector function, as you ask the question, we're going to have a dot product, and we can say this as a divergence. Similarly, since it is a vector, we can also have a cross product, and then we can say this as a curl, and this has a physical meaning. Okay, and what those physical meanings are, I'm going to just tell you in a while. But is this question clear to you? I mean, the question which you asked.
Yes, sir.
Okay, so you see, you ask simple question that what is going to happen if it acts on a vector. So when it acts on a vector, we have to take like a dot product and cross product, and then this dot product is basically showing you the divergence, and this cross product is basically going to have a curl, and I'm going to give you the physical meaning of that just right now. So first of all, let's go for the divergence. So when you calculate divergence, you can write, because delta was defined something like this. So x cap del over del x plus y cap del over del y plus z cap del over del z. Then dot product of V, where we can say that V is a vector with a component Vx, Vy, Vz, and we can always
Excuse me,
write
sir.
this. Yes.
Sir, why can't we have del plus V, del minus V?
Sorry, can you repeat? Del plus?
Means del plus V, del means V cross, means cross product we take dot product also, or otherwise we take a scalar also, means a gradient, divergence, and curl.
Yes.
Then
Yes.
why can't we take, sir, del minus V, or del
Yes.
operator minus V means,
Exactly.
or del
Exactly.
operator.
Because yeah, and that's the definition. That's the crux of the whole thing. You know, that it is not an ordinary vector. Okay. So that's
Okay, sir.
distinguish it from an ordinary vector where you can have this as a, that's why we are calling it as an operator. We are not calling simply as a vector. We are calling del operator. Okay. So when we say operator, that what that means, that it is going to operate on something. You understand? Yeah.
Yes, sir.
And similarly, this differential are going to give you a more formula based thing, which you basically do in your simple calculus. That when you have a multiplicative, for example, you take the derivative of two functions, then you generally, take one constant and differentiate other, and then sum up with, vice versa. So these operators are also have some property like that, but different from the ordinary. And that is why you see the terminologies which we used. And that's why I wanted to be very clear that we say here ordinary derivative. Okay. But now we are talking about gradient, we are talking about the del operator, and we mentioned that this is a vector operator and this is not a vector, simple vector, as like an ordinary vector. Okay. So
Yes, sir.
these things to be very clear in our mind. But it's good that you have asked this question. Okay. Very good. All right. So then let's come back to what I wanted to discuss here. So when we say this, what is going to happen? You can visualize what we can write. What could be the result of this dot product of this?
Del Vx by del x plus del Vy by dy plus del
Right.
Vz by
Because
del
simple,
z.
yeah, because this is simple dot product, and then we can simply use the unit vector products, dot products, and then we can write something like this. And what is the physical meaning of this? So it is something like this figure. Okay. So you are calculating some field point, let's suppose here, and this field point is basically very dense at near to the origin, but then it diverges and it get fed up. Okay, so something like that. So divergence means something like something which is blowing up, or which is basically changing with respect to some point. Okay, so you can, and we're going to see the physical meaning of that very soon once we, and actually this is the electrodynamics part, so I'm going to give you many more examples with respect to the electric fields and magnetic fields, that what this divergences means. And initially, if you had also seen Maxwell's equations, where we also use this delta, this kind of things. So I will discuss those. But yes, again, I'm repeating that based on this, you should have a more and more numerical problem, which you must solve by yourself and discuss in the mathematical physics classes. And obviously, Dr. Rohit is going to give you all the details of all the calculations. So let me go for the curl part as well. And the curl part is again can be written simply like the cross product which we did. So you have x cap, y cap, z cap, and then determinant form. You can write del over del x, del over del y, del over del z, and then this v is like vx, vy, vz, and then simple multiplication is going to give you a vector again. Okay. So, and what physically that means? This means something like, if something like is going like swirling. Okay. So it is just like moving with respect to this origin. You can see this vector is rotating, and in this rotational plane basically, so if you have a 0, that means there should not be a rotation like that. And you might have seen these this, and these are called something like vector fields. and we're going to describe it again in terms of the electromagnetism, that why this cross product or the curl of this del operator is going to be very, very important for us. Okay, and based on that, again, you can make a lot of numerical problems, and this could be very useful for, I think, for the competitive examinations as well. So, please go through it in detail. Okay. All right. And then the fundamental theorem of gradients, which is just like an integral, which you know. So just for completeness, I'm just giving you this formula. So this gradient formula is just like an integral from A to B, and in the integral term, basically that how fundamental theorem works for the integration. If you have a function f which is dependent on some variable called x, and if you integrate it with respect to x, then it's giving you the boundary point, and you just take the subtraction. Okay, so similarly you can also talk about in the gradient term, like in the ordinary integral, and you can and we're going to see this in terms of electric field, magnetic field, that what we mean by this. Okay, and we will develop some of the theorems accordingly, and when times comes, I will come back again on these kind of fundamental theorems, and then I will describe you that what we mean by this integral. And so here just I'm quoting that when we say this type of things, we can say that is independent of path taken from A to B, like you might have learned in your basic 10+2 classes, where you talk about the potential, etc. And this is independent of path, something like that is going to be very important. So we will discuss now in terms of this del operator. Okay, so just for completeness, I'm giving you this, but when we'll in the next lecture, probably when we introduce electric field, I will talk about this in more detail in terms of the potential and all those stuff. Okay, similarly, the fundamental theorem of divergence should give you a delta dot Vt tau equal to, so this is a volume integral. So d tau is basically dx dy dz, and you can convert it into surface integral, where you can always have you can write delta dot V as V vector dot dA, where A is the area component. Okay, and in mathematical classes, you're going to have many more problems on that, and I think this should be proven also. These theorems are very important actually for your examinations point of view. Okay, similarly for the curl, we can change the surface integral into the linear integral, something like this. Okay, and when we discuss about Ampere's law and all those things, we're going to use these theorems very frequently. So I would suggest, so that's why this is just kind of advertisement that I'm going to show you, because we're going to use it in a very detailed manner, and this is a part of mathematical physics, so I'm not proving it one by one. Otherwise, your mathematical physics lectures make no sense, So that's why I just give you the overview of these things, and later on, we will use it more frequently, where we will talk about these things again. Another important thing is the curvilinear coordinates. Okay, so please be handy on that. You have to basically learn. So to just remind you, in your mathematics classes, you might have learned that there are something called polar coordinates. Like, for example, if you have a xy coordinate, okay. So I'm just reminding it that why we need this change of coordinates, etc. So in Cartesian coordinate system, you can say that this point is represented by, let's suppose, some coordinate x comma y. So we say this is a Cartesian coordinate, okay? But we can always change this and transform in terms of the polar coordinate. Okay, so let's suppose this is angle theta, which this coordinate point is making. Then we say that this xy can transform into a polar coordinate system. Let's suppose that this is r is the distance from origin to this xy coordinate. Then we say that x could be written as r cos theta, okay, and y could be written as r sine theta. So now you see, you define this Cartesian coordinate system into the polar coordinate system, okay. But sometimes we also need this to generalize in three-dimensional coordinate system, okay. So when we do it in a three-dimension, we do it in a spherical coordinate system. So now x is going to define like r sine theta cos phi, so which you can realize from here itself, that the two-dimension system which I just shown here, if I go with this notation, we just change this theta into phi, okay. So this theta is nothing but phi, okay. So if you just look at this surface, okay, so what you can do, I mean, let's suppose this is r, then you can say that this is x, and this x is basically defined as r cos phi, and this y is defined as r sin phi, okay. So you can see from here that if there is no theta, that means if there is no z-axis, r is going to lie in this plane, and then you remain like a polar coordinate system. But once you have another z coordinate, that means the three-dimensional object, then you have to have this extra term, which should be multiplied here. And this is very easy to find out. Now, please try by yourself. And if it's not, then in mathematical classes, you can obviously ask these things very frequently. And you need to remember these, by heart, by yourself. I mean, you can do this. So in a spherical coordinate system, we have x defined as r sine theta cos phi. We're going to use it very frequently. Similarly, y is going to use r sine theta sine phi, and z is basically r cos theta. It is very simple to understand from this, coordinate system. And also now this x, y, z, which was in the Cartesian coordinate system, is going to transform into another unit vector. Now in a spherical polar coordinate system, we have a theta cap, r cap, and phi cap, okay. So you have to represent any vector A in terms of these unit vectors, which you can do like this. So vector A is now ARR, which is called a radial component. This is a polar component, and this is called azimuthal component, okay. So with the corresponding unit vector in that direction. And then you have to transform this unit vector in terms of the Cartesian coordinate as well. You should know this thing, that how to do this. And these calculations are very, very important. Maybe it will take 1 or 2 pages of derivation, but you people should do it by yourself. And if it's not clear, obviously in mathematical physics classes, you must ask those questions, okay? And if it's again not clear, please frequently ask these questions to me. I will try to explain it everything one by one again. Similarly, in this spherical polar coordinate, you have to change the gradient, and then you see that now gradient is changed in terms of the radial, polar, and azimuthal component. And now you see the factors are coming here. So you have 1 over r delta t by delta theta, which was just like delta t by delta y. Now theta component also involved this 1 over r, okay? And similarly, the phi component involve 1 over r sine theta. So these factors, how these factors basically comes about, okay? So please do these mathematical calculations, and this is going to be very, very useful in all type of exams. Similarly, for the divergence, you can derive this quantity, and for the curl, you should define something like this, okay? And with the other thing, I will try to end today's session, because already we passed a lot of time. So in cylindrical coordinate system, so cylindrical coordinate system is nothing but something like, spherical coordinate system was something like this. So you have a sphere, but in cylindrical coordinate system, you have something like cylinder, okay, something like this. And this kind of problem we're going to solve in terms of electric and magnetic field. So you have this axis, okay, and then you have these 2 axes accordingly. Here also you have these axes, okay, but now the transformation is a little bit different. So once you define some point here, for example, then you have to define the cylindrical coordinate system. However, in spherical coordinate system, if you have something like here, you have to define what we said just before. Okay, so you have to have these transformations accordingly, and please try to go through it by yourself. And if there is any problem, obviously I'm repeating again and again, but please go through it in mathematical classes as well, because we're going to use it very frequently in the advanced stage. So with that, I will end today's session. But before that, if you have any question, please ask, and I will try to, give you the answers. However, let me just also tell you that there are more things like a Dirac delta function. We have to also use one-state functions and also vector fields, etc. But once the times comes, then I will describe those things along with the examples, along with the formula, which we basically developed for the electromagnetism part. Okay, right. Any question? No?
Sir.
Yeah.
Sir,
Please go ahead.
sir, what did you tell that name of the last coordinates are spherical?
Okay, for the azimuthal, that's let me write it for you. Azimuthal. Okay, so you can say this AZI MUTHL. Okay, azimuthal coordinates. Okay. Anything else? I think also Jumi wants it to ask something, or sorry, I didn't. I'm unable to see the names, but anyway. So okay, that's nice. And I
Sir,
know
I
that.
think Jumi wanted to say.
Yeah.
Yes, sir. So I think Jumi wanted to say something.
Again, your voice broke. Can you repeat again?
Sir, I think Jumi wanted to say something.
Yeah. So yeah. Can Jumi tell what you wanted to ask? Or maybe if your network is poor, you can put things in the chat box. I can see the chat box. That's the problem. There is a network problem a lot. So okay, so Jumi said no. Okay, that's fine then. So I know that these things are very, very integrate, and it's take time to discuss those things. But please revise these sections, and you have a week of time. So I'm going to use these things very frequently. Yeah, with that note, thanks again for joining, and see you in the next session. But if you have still any question, I can take one or two questions again.